Welcome to the video lectures of mechanical vibration. In the previous videos we have seen damped free vibrations and how we are going to be deriving the equation of motion and what are the different types of the damping materials or the damping bodies are going to be controlling the exciting force of the system. So in this video lecture we are going to be discussing about the over-damped system. So this over-damped system, already we have derived that equation of motion for the free damped system. In that equations we are using to define the displacement of the system, and from that we are substituting in the equation of motion, and then we are calculating the damped natural frequency of that particular system. So in this case, so the first one, the damped over-damped system, the x is equal to the displacement of the vibrating system, and a1 that's equal to a1 e to the power of lambda 1 t plus a2 e to the power of lambda 2. So in this case, as we have seen in the last video lecture, and the lambda 1 and the lambda 2 are the roots of that system. In the second one, a1 and a2 are going to be the arbitrary constants. So as we have that lambda 1 and the lambda 2, we do have that equation, from that we can calculate. And similarly a1 and a2, how we are going to be calculating, that's we are going to be checking. So in this case what will happen? So when we are going to say the system is going to be over-damped system. So in this case we know that we are using that symbol when the epsilon is going to be greater than 1. Here the damping ratio or the damping factor of the system is going to be more than 1. Then we can say that system is going to be over-damped. Then what will happen then? So in this case the motion is going to be a periodic motion. It is not going to be a periodic motion. It is going to be a periodic motion. That means that motion cannot repeat by certain interval of time. It will take different intervals of time to complete the different cycles. So that's why we are going to say that's the aperiodic motion. Then why? What is the cause to get the aperiodic motion to the vibrating system? That's because the mass moves very slowly. Due to this reason, the cycle is not going to be taking different times. So that's why the mass is going to be moved very slowly. So then what will happen? So the system comes to equilibrium in exponential manner, right? So that's already we do have assumed that in the damped vibrations that excitations of the system is going to be taken in exponential way. Similarly, the system is going to be come back to equilibrium position also. It will take the exponential manner, it will come back to its original position. If suppose any excitation is going to be coming to that system to vibrate, so then what will happen? To come back to its mean equilibrium position, the system will take a lot of time. That's going to be say infinite time to come back to equilibrium position. Alright? So in this case it will take a lot of time. So that's why we are saying this is going to be an over-damped system. So the next, how to calculate the A1 and A2 values? As you know that A1 and A2 are the arbitrary constants, right? These values can be defined or can be found from the initial conditions of the system. In this equation, particularly in this equation, which parameters are going to be slowly vary? As we know that A1 and A2 are the parameters that we need to calculate, and the lambda 1 and the lambda 2 we do have that equations of that. So then see the lambda 1 and the lambda 2 values, and the t is going to be the variable parameters. If I am going to be making equal to 0 so that I can calculate it. So then if I am going to be substituting t equal to 0 in this particular equations, then what will happen? This e to the power of 0 and e to the power of 0. Then finally we are getting the initial conditions of the displacement of the system, that is equal to a1 plus a2, right? In the single equation two unknowns are there, so that we are taking the velocity of that vibrating system also we are going to be considering here. So then the values of the a1 and a2 are negative. Suppose in this case x0 is equal to a1 plus a2, this total magnitude if we got it in a negative, then what is the indication of that? The value of the displacement x goes on decreasing with time. It means that amplitudes are going to be slowly, it is going to be decreasing. If this is going to be the positive, then what happened? It is going to be overshooting from the mean or equilibrium position. So then it's going to be negative, means it's going to be decreasing with the time. So then what happened? I am going to be deriving this equation with respect to time. That's going to be t equal to 0. So then what I am going to be getting? A1 into this parameter, right? And into omega n, t is going to be cancelled out. So then what happened here? A2 and this parameter and the t. The e to the power of 0 means almost we are getting the one value. So this way we are going to be calculating the A1 and the A2 arbitrary constant from that system. So we have defined that x is equal to, that's initial condition, the displacement of the vibrating system is equal to A1 plus A2. If A1 and A2 are the negative, it means that the displacement of the system is going to be goes on decreasing. At the same time, we to identify this A1 and A2, that I am going to be taking the initial condition for the velocity also, then I got this equation, right? So the same thing, we are converted into the graphical way after the experimentation. So, but in our present video or in the video, we are going to be discussing that is in the theoretical way. So in this case, what will happen? The x-axis is y-axis is representing the displacement of the system or amplitudes of the system. So then x-axis is going to be representing the time parameter. So then what will happen here? At one point of the time, we had given the displacement to the system. So then what will happen? So in the displacement system, already we told that the system is coming back to its original position by the exponential manner. It means that the energy is going to be dissipate in an exponential way. So then only it will come in the exponential manner. So then can you see the vibrating of the system is going to be how it is going to be. That means the energy of the vibrating system is going to be taken by the damping body. So then it will going to become. But when it comes to the simple harmonic motion, then what will happen in the simple harmonic motion? So the vibrations are going to be more like this. So this is going to be the simple harmonic motion we have seen for the free longitudinal vibration. But when it comes to the damped vibrations, the figure is going to be representing how the energy is going to be disappear with respect to that time. So just before we have seen that the displacement of that vibrating system, how it is going to decrease. That means the exponentially how it is going to be decreasing, that we have seen. The same diagrams we have taken here, this is going to be the x-axis is going to be representing the time, and y-axis is going to be representing the amplitudes of the vibrations. Then in this case what will happen? So already we told that when the epsilon value is going to be greater than 1, then we can say that system is going to be over damping system. So in this case what will happen? So then we have taken here the graph. This is experimentally it has proved that. So then this curve is going to be representing epsilon is equal to 1. It means that the critical damping is equal to the damping coefficient of the system. Then we can say that is the critical damping. So then what will happen? More than this, can you see here the epsilon equal to 2, 5, 10 and the infinity it is going. Then we can say that system is going to be over damping system. So in this experimentally, it has proved that, but we are studying that as a theoretically. Thank you. I hope you people understand this one.